John Eichelberger from Alaska. So, John, the floor is yours. I give you the opportunity to present yourself.
Thank you. Yes, here I am, presenting myself. Hello. Again, for and my co-authors who are not here, Jan Lavely, who provides some credibility about thermal fracturing, and Jeff Tester, who provides some credibility about supercritical fluids. And I want to point out there are two M's in magma. Don't confuse it with MAGA, Make America Great Again. That's not it. This is something much more wonderful. Magma is wonderful. So I want to talk about, well, I think many people in this room will agree that superhot geothermal systems may be the next big advance in clean energy. Why? Because greater power output per well, greater efficiency and conversion because of higher temperature and conversion to electric power. And if this all works, then remote sites can be used using the developing high voltage DC technology. There are a couple of caveats. One is not to cast rain on anybody's parade, but I'll argue that proximity to magma is needed to be truly sustainable. If you compare the power that is sucked out by a power plant with your ordinary volcano, these eruptions look incredibly powerful. But if you average the power output over time, they're like a modest geothermal plant. So in any case, we really need to understand the magma hydrothermal connection. And we haven't done very well at that because basically geothermal people see hydrothermal system and forget the magma underneath it, and volcanologists and magma dynamics types see the magma chamber, and usually their cartoons don't even have a hydrothermal system. Well, there has to be a hydrothermal system, as a matter of fact, and that really not only does the magma influence and drive the hydrothermal system, but the hydrothermal system plays an incredibly important control on what happens to the magma body. It is the controlling factor in heat loss. So we also agree that tapping high enthalpy fluids is a worthy goal that would make geothermal energy more economically attractive, but fracture permeability in ductile rocks may be a problem. Well, let's compare very hot rock, say just below the melting point, with molten rock. First of all, hot rock is a poor way to store heat because it has low energy density. Although, of course, it has almost limitless volume, so that's a compensating factor. Another bad thing about rock is that it's really kind of an insulator, and the stored heat is difficult to access because of low thermal conductivity. So you have to have a big surface area between your rock, where the energy is stored, and the working fluid. Now, the working fluid has very high energy density, but it comprises a very small amount of the reservoir, depending on what the porosity is. Magma has an order of magnitude higher energy density, and the accidental encounters at Krafla, at Hawaii, and East African Rift suggest that which were never seen before by geophysics, before drillers bumbled into them or brilliantly encountered them, There may be a lot more magma down there than we thought. And all that heat stored can be accessed not by what we do, but by natural large-scale convection. So there are three processes to consider here. One is latent heat of crystallization, one is convection of magma, and one is thermal fracturing. You can calculate an effective heat capacity within the interval that magma crystallizes, which for silicic magma, which is what we're interested in here, is a fairly short interval. If it's close to being a eutectic, which doesn't really exist, but it's a nice word, so I thought I'd mention that. So with so heat capacity, that's the amount of energy you get out per degree of cooling, and what's happening here is that heat is released by growing crystals. So you have an order of magnitude higher heat capacity with an ordinary rock, and that translates for getting a certain amount of energy power over a certain length of time with a certain amount of cooling. You basically need an order of magnitude. You need an order of magnitude more rock than you need magma. For a gigawatt for 30 years, that's 10 cubic kilometers, and only 1 cubic kilometer for magma. By the way, there's about 31.5 years in a gigasecond. So if you're really healthy, you'll live to about 3 gigaseconds. If you're not so healthy, you might leave the scene around 2 gigaseconds. So we have to be careful. I'm in my third gigasecond, working on that. Okay, so basically, convection of magma and cooling and crystallization of magma makes it denser, and it descends, and it's basically going to pull uncooled magma up to the roof of the magma chamber. You can say, well, how much, it's a magical way to move heat. How big a plume of rising magma in the chamber do you need to deliver a gigawatt to basically the base of the hydrothermal system? And it's less than a radius of 20 meters of magma rising at only a centimeter per second. If you assume that only a tenth of the energy gets deposited here at the roof. Now we have some insight on what's going on here from longer ago than I care to remember, earlier in my career, 40 years ago, drilling into a proxy for magma chambers, lava lakes. And the wonderful thing is that these lakes were drilled repeatedly over a span of more than 20 years. This is a temperature gradient, and with depth down to about, well, the whole thing was about 100 meters deep, and the top here is around 1100 degrees Celsius. And you notice that instead of gradually a curve going like that, the simple conductive growth of a crust, you actually have this extremely steep thermal gradient propagating downward. So basically, you've got a lid on the magma system that is moving down at a constant rate. Why? Because fractures are growing because of the density change, the volume change with cooling, and the hydrothermal system is chasing down and making these fractures. It keeps chasing after the retreating heat source. So instead of building up a conductor here at the top, which would cause your power output to drop off at proportional to reciprocal of the of time squared, instead you get a linear thermal power output, because what's the rate limiting factor is conduction through that lid, and that lid is staying the same thickness. Well, we've had many wonderful accidents now of people drilling into magma. And by far the best described was IDDP-1, although even there, that's not the only hole that has hit magma in Krafla caldera. And what we do is we see the same thing. There's an abrupt change from relatively cold, like 350 C is pretty cold, over a distance of only, tens of meters or less, we go from brittle rock to crystal-free liquidus that is extremely hot magma. I think no one would have predicted that. That's not what happens in a lava lake. We see this same kind of thin lid, but instead we don't have a mush zone on top. I think that our hypothesis here is that that's because this thing is convecting, and rather than painting the roof with crystals, as soon as it gets a little bit denser, it dives down and is replaced with uncooled magma. So, and this is making use of the data from IDDP-1. There's an awful lot we don't know. We got these tantalizing, I shouldn't say we, because I wasn't part of that. I just admire it. We got partially melted roof rock and this pure, very hot magma, but there's no partially crystallized magma. That's gone. Also, because Icelanders like to drill blind, there's nothing below 270. So it's all no person's land. But you can see the importance of actually getting core out of here to understand this transition zone from the hydrothermal system to the superhot magma. That hypothesis would really change our view about how magma chambers work. Instead of crystallizing from the outside and building up a insulator around it, the cooled magma is accumulating at the bottom, and thermal fracturing is maintaining permeability and keeping this lid very thin, so it's maintaining the thermal output of the system. Now, what that means is that the distance between the magmatic heat source and the hydrothermal system is very important. If it's like hundreds of meters, which I think is what people imagined, because as I said, geothermal people never put a magma chamber underneath, and magma people never put a hydrothermal system above. Well, this translates into time, and it means that if you change something down here, you've got thousands of years before conduction is very slow, before there's a change up here, which basically means you're only mining old heat up here. So you got to keep drilling holes to make up for that. But what we see at Krafla is an extremely short distance between the hydrothermal system and magma, which implies a characteristic time for conduction of only a matter of years. So the magma down there, if it indeed is a big body, and I'm very bullish on magma, so I think it is, the magma down there already knows there's a power plant up there. And does the magma feel bad about that? No, it gets excited. It starts conducting faster because you're cooling off that top faster. So it's win-win. So here's how you get this wonderful system. You've got convection in the magma body. You've got thermal fracturing maintaining a thin distance to the hydrothermal system and permeability. You then have a high enthalpy plume, Sam Scott's high enthalpy plume coming off this thing, and fantastic transport of heat and efficiency in turning it into electricity. So, but suppose the magma isn't there, well, then, as I said, you've got to make things up with drilling, and things are not nearly as rosy. So the first step, and now for a word from our sponsor, the Krafla Magma test bed, our very first phase is to go for the low-hanging fruit that we saw, taught us a lot about magma from Kilauea Iki, which is to core continuously across that hydrothermal magma boundary, and at the same time put a string of thermocouples in there through the conductive zone. That will, for the first time, give the heat flux from the magma system to the hydrothermal system, which is as good as going to the moon as far as I'm concerned. Thank you.
Thank you very much, John. We have maybe time for one quick question from the audience. Yes, Hjalti?
Just a question of curiosity. This permeability along this magma, was it induced by the borehole or was it natural?
That's an excellent question. That's what somebody says when they don't know the answer. And it gives them time to think. No, I think it's quite possible it was induced by drilling.
Okay, I think it's a big question that needs maybe longer time to answer fully. We don't have time to that. Next one, I would like to inform you that we had a change in the program yesterday. This change has appeared on the website program, but I think it has not yet been uploaded into the app version. But instead of Mr. Ólafur Flóvens, the CEO of Iceland Geosurvey, who was planning to be the next one, he has been transferred to tomorrow morning. But instead, we will have a talk by Professor Andri Stefánsson at the University of Iceland, who's one of the leading geochemists in the world. And I actually think maybe that talk actually fits quite well in with following the talk of John Eichelberger. So, Andri, are you in the room? Yeah, here. You had moved. So, please.
I'm always moving. That's me. Okay. So how does it work? Okay, so hi everyone. Maybe many of you know me. Those of you that don't know me, I work at the University of Iceland. I'm a chemist. So maybe most of my work is not related so much to geothermal, but some of what we do actually has some very important implications to geothermal energy, and a little bit about what John was talking about here before. How do the systems work? So I'm going to talk about high enthalpy systems, or these super hot fluids, a little bit today. So we are very interested in this for many respects. Partially just because it's a part of a bigger system, the Earth's crust that starts in the mantle all the way up to the surface, and you have all kinds of things happening in between, magma movement, for example, and then often at the top you have geothermal systems. And we are particularly interested in the super hot fluids that people have been talking about exists actually below and close to the heat source, something that we are not used to think about. We are used to think about the upper part of the systems. And instead of talking about the magma and how this hydrology and heat is transported, I'm just going to talk about the chemistry. And we are interested in the chemistry, and I'm going to show you a little bit today how we can use the chemistry and how we can use things called isotopes to understand some of these processes. Isotopes are almost like fingerprints of processes and sources. It's like being a detective, okay? So it's a fingerprint method. So if you want to know where the fluid is coming from, where it's going, what it has seen, you can play the role of a detective. So I'm going to show you that a little bit today. The start of this actually comes from physics. It's many people, including there are people here in the room, I guess, like Sam and others, have been trying to explain what happens when you place a magma body into the upper crust of the Earth's crust. So I'm just going to show you this schematically. So what happens if you have a groundwater system and then you put a big body of magma into the system? To start with, nothing is going to happen. Just have a magma body in a groundwater system. And then when you start simulating this, taking into account all kinds of things, heat and fluid transport and so on, what you start seeing is that, of course, the magma starts to heat up the surrounding groundwater very close to the magmatic body, the heat source, and the thermal gradient is very steep to start with. So you develop something that we would call supercritical or super hot fluids, very close to the magma body, and then on the top of this you maybe have upflow, a little bit upflow of two-phase subcritical fluids, but at the surface you don't see anything. And then later on this system develops into a more conventional convection type system where you have advection towards the heat source, and then the fluid is shooting up to the top, but you still, close to the heat source, you have very steep thermal gradient and this formation of the super hot fluids. We are more used to think about this part of geothermal systems than this part, but this total system is actually the entire upper part of the crust. And eventually the heat source dies out, the magma solidifies and cools down, and our geothermal system somehow disappears. The time scale here, well, this is all relative. It depends on the fluid type, on the size of the intrusion, and many things like this, but we are talking about hundreds and thousands of years usually. This is a little bit where the physical understanding stands today. But there are issues with this when we think about chemistry, because we know that the magma doesn't only transport heat into groundwater systems to develop geothermal systems, it also transports fluids. And those of you that have somehow seen volcanic eruptions, you see this. You have the steam coming up, it's the fumes, it's mostly water actually, CO2, sulfur, chlorine, fluorine, all these different volatiles. So the magma is also transporting this into the systems. So the chemical perspective of this is somehow more like this. You have a heat source, you have the magma importing some volcanic gases into the geothermal system, you have super hot fluids that can be either the groundwater and or the magma volatiles, and then you have the convective system, geothermal system happening at the top. Well, I'm not a physicist, I'm a chemist, so I don't think like this, I think like this. Okay, this is a phase diagram of water, and what we are really interested in is how the chemical composition of the fluids actually vary as a function of something like this. Okay, so this is the same diagram like this one here, in a way. But here you have the pressure and the enthalpy of the fluid, and then the phases of water. So this would be liquid only, This would be the two-phase field. This would be the super hot field. This is the critical point here. Your magma is sitting. And you have these projected arrows like flow arrows of advection towards the intrusion, flow above the intrusion. And this would somehow correspond to heating up into a super hot fluid and then somehow cooling and condensing at the top through the two-phase field of the systems. So this is somehow what we were interested in. And the basic questions that we're asking, well, the fluid that is sitting here, where does it actually come from? Is it the surrounding groundwaters, or is it actually the magmatic fluid? Because if it's a magmatic fluid, you can think of like, that's very acid sometimes. This is, can be somehow difficult to harness and utilize, whereas this is maybe more of a conventional geothermal fluid. But the thing is, across this field, there are lots of reactions occurring. So it's very difficult somehow to trace this back. So that's where these isotopes come in. These are the fingerprints of these sources and these reactions. So the questions we are thinking about, where do the fluids come from? Well, this type of systems, they are not just made up on computers. They are actually observed in many, many places in the world. There are at least 25 deep wells that have encountered conditions like this. Sometimes people don't know about it. Sometimes people realize it afterwards. Sometimes we somehow are aiming for something like this. But probably the best example today of a fluid discharge of this type of a system is the ITDP-1. There are other places that people have been seeing similar things, but not discharges in the same way. So I'm going to use a little bit ITDP-1 as somehow a case study to show you how these techniques are actually being applied. It involves simulations and collecting lots of samples. You have to collect samples of the geothermal system, the groundwater system, and the volcanic system. And then you somehow have to mix this together. So it includes going to funny places like volcanic, fun places like volcanic sites, geothermal fields, and many, many other things. But most of the time that we spend is actually in laboratories like this, okay? So we take the samples and then we try to squeeze out these isotope fingerprints. And maybe 20 years ago, we couldn't do this. But there have also been advancements in this isotope analytical technique, so things we couldn't do, we can do today. One of the things that we have been using for a long time is to use the water isotopes, the heavy water, to trace the source of water. This is something we have been using since the 1960s. And this is just as a start one. You can see here that all these dots here and squares, open things, they are the values for the geothermal system in Krafla. These are just the groundwater source geothermal systems. And they've closely followed this line here, which is the rainwater line. So what does this mean? It means that the water at Krafla is just the local rainwater. It's just rain in and up. And where does the ITDP fluids lie? Exactly at the same spot. So ITDP, wherever if we injected it in or if it locally rained, this is as another thing, but the ITDP-1 fluid is just the local geothermal groundwater. And magmatic fingerprint lies here. There's no signs of that. There's no magmatic water going into these systems, at least for this particular system. We go to the next element. Funny thing now, the fingerprint is called chlorine-37. It's a chlorine isotope. It's a complicated thing, but don't worry. This is the groundwater systems. There's diamonds here. The ITDP fluids are the green squares exactly at the same place. This is just a local geothermal system. It's actually the chlorine is coming from the rock, whereas a gas, that's sitting somewhere at, I don't know, floor 10 in this building. Okay, it's really a high positive value. There's no magmatic chlorine in the ITTP. It's just the local groundwater again. Go to sulfur. This, I know this is even more complicated. This is the next fingerprint. It's the same conclusion. It's just the local geothermal groundwater. And when you look at them all together, it actually maybe becomes relatively obvious. So we are using the fingerprint methods of some of these key volatile elements and some of these key isotope things. And this is just a volcanic gas. This is ITTP1. This is Krabla. And you can, the conventional geothermal subcritical or fluid, and this would be the ITTP1 superhot fluid. And you can see that they're almost identical, whereas the gas is very different. When you go to the isotope, sometimes there's an overlap, but here you see oxygen. This is very similar to the geothermal fluid, which is of rainwater origin. This is the magmatic fluid. Chlorine again, same here. Sulfur is a little bit difficult. So where does this stand today? Well, superhot fluids or supercritical fluids, whatever you want to call them, they form around magmatic intrusions. Physicists have been telling this to us for 50 years. But maybe advancements in the last 10 years have really somehow convinced some of us, including me, that this must be going on. And this is simply because of conductive heating of the magmatic body to the surrounding groundwater. But you can also have a magma degassing into the systems. And we know that some of these volcanic systems that we see at surface are dominated by this. ITTP1 in Krabla, this is the case where you almost have no magma gas coming into the system, and it's just a conductive heat from the magma body to the surrounding geothermal system that is forming the superhot fluid. It's kind of a nice thing because it means that there's a lot of nasty stuff in there. We are also thinking that we have often in other systems magma input, magma gas input, and we are applying the same methods. This was probably the case also in Krabla in the 1980s, and this is definitely the case for many, many similar systems in other geological locations. So what are we doing today? We're just doing exactly the same thing, but just for other geothermal systems. These are not necessarily always systems that people are thinking of drilling for super hot systems, but they are thought where we have magma bodies at shallow depths, high magma degassing, low magma degassing, and so on. So we have been in Greece and Italy, quite a lot in New Zealand, down in Kenya, but we're also again going into some of the systems that we know we have a recent magmatic body at a shallow depth within the systems, for example, Askja, even though there are no intentions of drilling there. Lots of people, some are in the room here, at least I've seen Sam, and then I'm here when I was young and pretty, and thank you very much.
So thank you very much to Andri, who is not as young, but still as pretty.
I'm glad.
Any question to Andri? Yes?
The chlorine input to the basalt was recent seawater. Would you expect the same high value to the Delta 37 chlorine?
So,
Or would it possibly look meteoric as well?
yeah, exactly.
So if it's recent, that wouldn't apply then?
No, so if it's seawater input, okay, and there is no gas scrubbing, then you would get the same value. Seawater is a difficult thing. Yeah. But you would have a very different sulfur signal then. So it's the combination of everything. Okay? It's like the same thing as a detective. You use fingerprint DNA and it goes on, and if it all points to the same thing, that's your conclusion. Okay? More questions? I'm off the hook.
Okay. So thank you very much. I think this was a very valuable and good input, and